Hello everyone, myself Swati and I have done my graduation from Guru Zimbabwe University of Science and Technology, Hisar, Haryana, and currently I am pursuing a master's degree in chemistry at Indian Institute of Technology, Jodhpur, and today I am going to explain a very important topic in inorganic chemistry, which is CFT, crystal field theory, and as written here, CFT describes the breaking of degeneracies of transition metal complexes due to the presence of ligand. What is means by degeneracy? Degeneracy is a word which is the orbitals, like the orbitals having the same energy, all the orbitals having the same energy, and there are two assumptions of crystal field theory, and which is first is it is a model used to describe the bonding in transition metal complexes, and by assuming the bonds are purely ionic and electrostatic in nature, which is written like metal which is electron deficient in nature, and ligand which is electron rich in nature, and these two are having purely ionic interaction. And the second assumption is central metal atom and the ligands are considered as point charges. And the next topic we should know for understanding the CFT is complex formation. Complex formation, these are of two types. Complex formation means a metal ligand complex, which is primary interaction, and secondary interaction. Like as earlier explained, this is a metal, electron deficient in nature, and this is a ligand, electron rich in nature, and this is placed at infinity distance from metal ion. And in case of CFT, every ligand has its own crystal field. And as ligand approaches metal from far field, there will be attraction between metal and ligand, and that is known as primary interaction. This is attraction between metal ion and ligand. When ligand is at far field from metal ion, and when the ligand comes more closer to metal ion, there will be a repulsion between ligand and metal, and that is known as secondary interaction. So this is repulsion between ligand crystal field and metal ion. When ligand is very close or in near field with metal. With metal ion. So this is the complete mechanism of the complex formation, and as we move forward in CFT, as this is a topic of transition metal complexes contains d and f orbital, and here we will talk about d orbital. D orbital which has 5 suborbitals. Total number of orbitals in d orbital is 5. First is dxy, dyz, dxz, dz square, and dx square minus y square. And the shapes of these orbitals are as follows. First is dxy. First make the axis of like x-axis, y-axis, and dyz, dzx, dz square, and dx square minus y square. So these three are having lobes in between the axes. And these lobes along the axis. So these lobes are in between the axis, and these orbitals are known as T2G orbitals. And this is a dz square orbital, and x. So these have their own lobes along the axis, and these orbitals are known as EG orbitals. On the basis of these d orbital complexes, I will explain the crystal field splitting in octahedral complexes. Crystal field splitting field splitting in octahedral complexes. Octahedral complexes means coordination number 6. Coordination number 6. So in this, ligand approach from ligand approaches towards metal ion along the axis. Along the axis means these two orbitals are having the lobes along the axis, and these three orbitals are having their lobes in between the axis. Means these orbitals will experience more repulsion than these orbitals, which I explain in this part. This is the d orbital. Degenerated d orbital of free metal ion. As ligand approach from far field to our d orbital, it will experience a repulsion from ligand, and it will have a slight increase in energy but remains degenerate. So this is average energy of d orbital in spherical crystal field. After that, when ligand comes more near to metal, as I explained, these orbitals are having their lobes along the axis. So in octahedral complexes, ligand comes toward metal along the axis. So these will experience more repulsion, and these will be higher in energy. These are Eg orbital, and these will feel repulsion but lower than these Eg orbital. So these T2G orbitals have lower energy. T2G. This is delta O CFSC. CFSC means crystal field stabilization energy, the net stabilization energy which the d orbital gains after the splitting of their degenerated d orbitals. This is barycenter, and the redistribution of energies in case of octahedral complexes are plus 0.6, and here and here minus 0.4. Split it, d orbital in case of octahedral complexes. So now in case of tetrahedral complexes, this is just opposite to octahedral complexes. In tetrahedral complexes, coordination number is 4, and ligand approach toward metal ion through in between the axes. Metal ion from in between the axis. Coordination number is 4 in case of tetrahedral complexes. So this will remain same in case of tetrahedral as octahedral, and as I explained, ligand approach toward metal ion from in between the axis. So these T2G orbital have their lobes in between the axis. So these will feel more repulsion than Eg orbitals, and so they have more energy and they have lower energy. T2 and Eg and E, and this is delta T CFSC in case of tetrahedral complexes. And why there is no G in this case? Because tetrahedral complexes does not have any center of inversion. That's why there is no G in case of. And the redistribution of energy in case of plus 0.4 and minus 0.6. So this is the lipid d orbital in tetrahedral complexes. And now we can understand the concept of CFT with the help of an example. As the complex is FeCN6 4 negative, and as there are 6 ligands, so it's a octahedral complex, and this will be the splitting diagram of octahedral complexes. So there is a Fe, and the oxidation state of Fe we can find from here. Fex minus 6 equals to minus 4, and x is equals to plus 2. So Fe is in plus 2 oxidation state in this complex. And what is the atomic number of Fe? Which is 26 atomic number. And the electronic configuration of Fe is argon 4s2 and 3d6. And Fe2 positive, then 4s2 releases electron as it is lower in energy than 3d. So it will release its electron. So Fe2 positive electronic configuration is argon and 3d6. So there are 6 d electrons which will be filled in these splitted d orbital diagram of octahedral complexes. This is T2G and this is EG. So as it is 1, 2 and 3. So and the next electrons are also filled in this, as Cn is a strong field ligand. Strong field ligand means the ligand interacts strongly with metal ion, and this will be found with the help of spectrochemical series. So, and these strong field ligands have delta O greater than pairing energy. Pairing energy means the energy which we have to give the complex to put the electron in the same orbital. So this will be the electronic configuration T2G6 of this complex. And what is the magnetic behavior of this complex? So all the electrons are paired, so it is diamagnetic in nature. What is the spin of this complex? As it is a strong field ligand and all are diamagnetic, all are paired electrons, so it's a low spin complex. Low spin complex. And what is the color? And as CFT is used to define the color of the complexes, but these this complex is diamagnetic in nature, means it does not have any unpaired electron, so it is colorless in nature. Colorless. And if we found out the CFSC delta O of the complex, that means 6 electrons are in this T2G orbital. Plus there are no electron in EG, so 0. So this is minus 2.4 plus 0. So overall minus 2.4 is the CFSE of this complex. And this is the concept of CFT. Thank you.